Hello, welcome to another module in this massive open online course. So, in this module, let us look at a special class, or rather classes of matrices termed rotation and unitary matrices, which arise very frequently in linear algebra and matrix algebra, right. So, let us look at special classes of matrices. These are the rotation, and we also have the unitary. Rotation matrix and unitary matrices. Rotation and unitary, and these are special kinds, or you can think of as classes of matrices. Now, the rotation matrix parameterized by theta, what we call as a standard form rotation matrix, R of theta, this is what we call as a parameter, or basically a free variable, right. That is, theta can vary independently, and depending on that you have the matrix. Alright, the different elements of this matrix depend on this parameter theta. So, R of theta, this rotation matrix, is essentially, this is a 2 cross 2 matrix. We are looking at the 2 cross 2 rotation matrix. 2 cross 2 rotation matrix, this is given as cosine theta minus sine theta and sine theta cosine theta, and the rotation matrix satisfies rotation matrix, this R of theta, this basically you can show corresponds to rotation of the coordinate system. Anti-clockwise by theta, that is, if you have a point, correct, if you have a point x bar, and these are your this is your current coordinate system, and then you rotate this anti-clockwise by theta, and what are the new coordinates? These are essentially given by the rotation matrix, right. So, this is rotation anti-clockwise by theta. Let me just draw this. That is, if you have a system that is rotated by theta, the new coordinates are given by taking the old coordinates and multiplying them by r theta. Anyway, the rotation matrix satisfies the property, note r theta, I am going to simplify simply denote this by r, satisfies the property that R transpose into R equals R transpose equals identity. This is the interesting property that the rotation matrix satisfies, that is R transpose into R into R transpose is identity, which means that R transpose is R inverse, that because this is a square matrix. So, this means R transpose is essentially R inverse, that is the inverse is obtained simply by taking the transpose of this matrix. So, let us look at this. R transpose into R equals, you can check this, cosine theta sin theta minus sin theta cosine theta times R, which is essentially cosine theta minus sin theta So, the 1 comma 1 element, if you simplify this, you can clearly see the 1 comma 1 element, this is cos square theta plus sin square theta. So, this will be cos square theta plus sin square theta, this is minus sin theta cos theta plus sin theta cos theta, which is 0. This is again minus cos theta sin theta plus sin theta cos theta plus sin theta, and finally the last element is 2 cross 2 element is sin square theta plus cos square theta, which is 1, and this element once again you can see this is also 0, and so this reduces to, it is not difficult to see, this reduces to the 2 cross 2 identity matrix 1 0 0 1. So, this is the interesting property of the rotation matrix. So, R equal to, so R transpose equals R inverse, and similarly you can also check we checked, I think R transpose R, similarly you can check R transpose equals identity, and you can also see this by the fact that the inverse of a square matrix is unique. So, if R transpose is the left inverse, that is R transpose R equal to identity, then it must also be the case that R into R transpose equals identity. Okay. So, this is an interesting example. Now, the analog of that for complex matrices is not what is known as a unitary matrix. So, unitary matrix is the analog, I would say roughly speaking, is the analog of a rotation matrix. So, I can think of this as, loosely speaking, a complex rotation matrix. This is what it is. This is a complex rotation matrix which satisfies the property. You must have, since R transpose is identity, the unitary matrix U, I replace the transpose by the Hermitian, then this is U Hermitian equals U Hermitian U equals identity for any unitary matrix U. So, a unitary matrix U satisfies the property that U Hermitian equals U Hermitian U equals identity. For example, you have, let us say, a canonical example is, you can write a complex unitary matrix. This will be a product of, this will depend on now more parameters because it is complex. So, this will be e raised to j phi 1 cosine theta, e raised to j phi 2 sin theta minus e raised to j phi 2 sin theta and e raised to minus j phi 1 cosine theta, and you can see this depends on 3 parameters, phi 1, phi 2, theta. This is the matrix that depends on 3 parameters, phi 1, phi 2, phi theta. And you can once again check U Hermitian. If you have U Hermitian, let us write U will be e raised to j phi 1 cosine theta e raised to j phi 2 sin theta minus e raised to j phi 2 sin theta e raised to minus j phi 1 cosine theta times the product U Hermitian. So, U Hermitian will be e raised to minus j 1 phi 1 cosine theta. So, you take the transpose and Hermitian, right. So, minus e raised to minus j phi 2 sin theta e raised to minus j phi 2 sin theta e raised to j phi 1 cosine theta. And if you multiply this will be, you can once again see the diagonal terms will be cosine square theta plus sine square theta, and this will also be sine square theta plus cosine square theta. Off diagonal terms will be, that will be, if you look at this, minus that will be minus e raised to minus j phi minus e raised to minus j phi 2. I think this should be, there is a problem here. There has to be a minus sign over here. There has to be a minus sign over here. So, this will be minus e raised to minus j minus e raised to, and therefore, once you do this, this will be e raised to. So, there is a negative sign over. So, there is no sign over, negative sign over here, and this will be minus e raised to minus j phi 2 plus phi 1 phi 2 plus phi 1 sin theta cosine theta plus e raised to minus j phi 2 plus phi 1 sin theta cosine theta, and therefore, this is obviously going to go to 0. And similarly, here you will have minus e, that is the 1 comma 2 element, minus e raised to j phi 1 plus phi 2 cosine theta sin theta plus e raised to j phi 1 plus phi 2 sin theta cosine theta. And you can clearly see that this will also be 0, and therefore, this will be the identity matrix. Again, this will be 1 0 0 1, which is essentially the identity matrix, right. So, this will be just doing one final check, e raised to minus j phi 1 cosine e raised to minus j phi 1 minus e raised to j phi 2 sin theta e raised to minus j phi 2 sin theta e raised to j phi 1 cosine theta. So, this is going to be this. Alright, you can check this, and if there are any typos, you can correct this so as to ensure that this is essentially correct. Okay. So, just make sure that what we have written over here, it should be by and large correct, but if there are any residual typographical errors, then please check this. Okay. Now, therefore, and as I told you, these are very practical. For instance, one place where they arise, for instance, some of you might have heard in the context of modern wireless communication, we have codes, right, especially when you have wireless systems with multiple antennas. One such code is what is known as an Alamuti code, right. I will just briefly describe this example because this arises in practice, right. So, you have the Alamuti code, and in this Alamuti code what you have is you have the receiver with a single antenna and you have the transmitter with two antennas, and these are the channel coefficients H1, H2. So, this is the receiver, this is the transmitter, and these are the channel coefficients H1, H2. H1, H2, these are the channel coefficients, and what you can see is that is basically, if you see this is a 2 transmit antenna system, number of transmit antennas equal to 2, and number of receive antennas equal to 1. And the channel matrix for this system, if you look at this, is what we call as the effective channel matrix for the Alamuti code. Effective matrix, channel matrix, we can call this effective channel matrix. Effective channel matrix for the Alamuti code. This is given by the expression H1 H2 conjugate minus H1 conjugate. Now, this by itself is not unitary, but if you look at H tilde, which is obtained by dividing the matrix by the norm of the channel vector, that is norm of H bar, that is if you look at H1 H2 conjugate minus H1 conjugate. Now, this matrix H tilde you can show easily is a, in fact you can check this matrix you can easily show this is a unitary matrix, that is H tilde Hermitian H tilde equals H tilde Hermitian equals 2 cross 2 identity matrix, and in fact this quantity norm of H, this norm of H bar, this is also obvious, this is square root of, this should be fairly easy for you to understand, this is the norm of each column, that is norm of h bar equals square root of magnitude h1 square plus magnitude h2 square. In fact, this is a practical example of this concept, and in fact rotation and unitary matrices arise very frequently. Especially we will see a concept later on in this MOOC where we will talk about, for instance, the singular value decomposition. And in the singular value decomposition we have unitary matrices, right? We have the singular vectors, and essentially we will see that the unitary matrices are a key component of the singular value decomposition. Okay. All right, let us look at some properties of these unitary matrices. Unitary matrices are very interesting properties, and as I said, they arise very frequently and they have very interesting properties. So, properties of unitary matrices. For any unitary matrix U, it is easy to show that the determinant of U or the magnitude of the determinant of U equals 1. This is not very difficult to show, because remember, for a unitary matrix, and this is not easy to show because remember we have the property UU Hermitian equals identity. This implies that determinant of UU Hermitian equals determinant of identity, which is equal to 1, but the determinant of the product of two matrices is nothing but the product of the determinants, determinant of U into determinant of U Hermitian equal to 1. This implies, but determinant of U Hermitian is the conjugate of the determinant of U, that is a product of property of the determinants. So, this is essentially, you can write this as the determinant of U times determinant of U conjugate equal to 1. This essentially implies that magnitude determinant of U square equal to 1. This implies magnitude of determinant of U is equal to 1, right. So, magnitude of for any unitary matrix, the magnitude of determinant U is equal to 1. In fact, you have an even more interesting property, that is, if you look at any eigenvalue of the unitary matrix, that has to have the magnitude equal to 1, right. All eigenvalues of unitary matrices have unit magnitude. That is a very interesting property. So, let lambda be eigenvalue of U, then magnitude lambda is equal to 1. This is an interesting property. For instance, let us consider V bar to be, since we are considering U to be matrix, let us say let us call Z bar be the corresponding eigenvector. This implies U times Z bar equals lambda times Z bar, and this also implies that Z bar Hermitian, U Hermitian, taking the Hermitian on both sides, this is lambda conjugate Z bar Hermitian. Now, multiplying LHS and RHS in both 1 and 2, multiplying left hand side right hand side in 1 comma 2, this implies we have z bar Hermitian u z bar equal to lambda conjugate z bar Hermitian z bar into lambda. This now we have u Hermitian u equal to identity. So, this implies z bar Hermitian times z bar equals lambda conjugate into lambda, that is magnitude lambda square into norm z bar square, and on the left also you have norm z bar square, z bar Hermitian z bar. So, norm z bar square equal to magnitude lambda square norm z bar square. This implies magnitude lambda square equal to 1. This implies that magnitude lambda equal to 1. So, all eigenvalues of the unitary matrix have unit magnitude. This shows eigenvalues of the unitary matrix, these have unit magnitude. And let us look at another interesting property. We have u Hermitian u equal to identity, which means we write it in terms of the columns, that is, if the matrix U has the columns u1 bar u2 bar, if we say the unitary matrix has the columns u1 bar u2 bar un bar, let us say this is an n cross n matrix, then the u Hermitian will automatically have rows u1 bar Hermitian, u2 bar Hermitian, un bar Hermitian. And this implies that if you look at the product, this will be of the form, well, the diagonal entries will be u1 bar Hermitian, u1 bar, u2 bar Hermitian, u2 bar, and so on, and the off diagonal elements will be u1 bar Hermitian, u2 bar, u2 bar Hermitian, u1 bar, and so on. And these are the diagonal entries are 1. So, and this is equal to identity, right? And what is identity? Identity is nothing but a matrix which has all the diagonal entries which are 1 and the off diagonal entries are 0, right. So, this implies essentially that ui bar Hermitian ui bar, which is equal to norm ui bar square, which is equal to 1, and ui bar Hermitian uj bar equal to 0 if I not equal to j, that is off diagonal entries are 0. So, diagonal entries are 1. So, if you look at the diagonal entries of this matrix, right, diagonal entries are 1, and if you look at the off diagonal entries, what are that is the 1, 2, where I j elements where I is not equal to j. So, if we look at the off diagonal entries, so off diagonal entries are 0, that is I j elements I j such that I j equal to 1, which means that if you look at any columns, if you look at the columns u1 bar, u2 bar, un bar, this satisfies the property that norm ui bar square equal to 1, that is their unit norm, and any two different columns ui bar and uj bar satisfy the property ui bar Hermitian uj bar equal to 0, that is any two different columns are orthogonal. So, we say the columns are orthonormal, they are unit norm and orthogonal. So, we basically have these two properties. So, ui bar, the columns ui bar are unit norm, they are unit norm and orthogonal, and this implies they are essentially this is what is termed as orthonormal columns. So, unitary matrix has orthonormal columns. Okay. So, this is an interesting property. So, unitary matrix has unitary matrix is orthonormal columns. Similarly, you can show it's not very difficult to say again, rows are also orthonormal, that is they have unit norm, that is the rows of the unitary matrix also have unit norm and they are orthogonal to each other. Now, let us look at another interesting property, and all these properties, these arise very frequently. That is, we take any vector x tilde, n dimensional vector n cross 1, which is given as u times x bar, where u is n cross n unitary matrix and x bar is n cross 1 unitary vector. Then if you look at norm of x tilde square, that is equal to x tilde Hermitian x tilde, which is x bar Hermitian u bar Hermitian u times x bar, which is now you can see u Hermitian u is identity. So, this is simply x bar Hermitian x bar, which is equal to norm of x bar square. So, it implies that norm of x tilde, this interestingly implies that norm of x tilde equal to norm of x bar, where x tilde equal to u times x bar. That is, if you multiply any vector by unitary matrix, it does not change the norm, that is the norm of the output vector will be the same as the norm of the input vector, and this is expected because u is simply a complex rotation matrix. This can be thought of a complex rotation, right. So, multiplying by unitary matrix does not change, leaves the norm invariant. Multiplication leaves the norm invariant. And further, you can also have another interesting property, that is, let us go back, consider our IID Gaussian random vector, that is x bar, which is distributed as Gaussian, mean equal to mu and variance is sigma square I, that is covariance is proportional to identity, sigma square times identity arises when the Gaussian components are 0 mean, are independent, and these are identically distributed, each has variance sigma square. So, this essentially implies that expected value of, or let us call this as x bar. So, expected value of x bar equal to 0, expected value of x bar Hermitian equal to sigma square times identity. Then now, if you have x tilde equal to again u times x, it is not difficult to see that expected value of x tilde equal to expected value of u times x, which is equal to u times expected value of x, which is equal to u times 0, which is equal to 0. So, expected value of x tilde is 0. Further, if you look at the covariance matrix of x tilde, that is expected value of x tilde Hermitian, that is equal to expected value of u times x bar x bar Hermitian times u Hermitian, which is u, now expected value of x bar Hermitian into u Hermitian, which you can essentially say is u expected value of x bar Hermitian is sigma square times identity times u Hermitian, which is now take sigma square outside u Hermitian, which is sigma square times identity. So, you have now expected value of x tilde, that is mean is 0, and covariance is again exactly the same, expected value of x tilde Hermitian equals sigma square times identity. And therefore, if you look at this, x tilde is proportional to is or has the distribution multivariate Gaussian. Now, since this is a linear transformation, x tilde is also, you can see, multivariate Gaussian. Because we said, as we have seen earlier, that is linear transformation of a multivariate Gaussian gives another multivariate Gaussian. And what is striking is that you have independent identical Gaussian, you have a Gaussian multivariate Gaussian with IID Gaussian component, Gaussian elements, and when you transform it with the unitary matrix, what you will see is again in the resulting multivariate Gaussian, the components are independent identically distributed Gaussian random variables with mean 0 and variance sigma square. So, the multivariate Gaussian, right, with independent identically distributed Gaussian random variables under unitary transformation results in another multivariate Gaussian with IID Gaussian distributed component. So, this is an interesting property, right. So, x tilde also has IID Gaussian elements, mean equal to 0 and variance equal to sigma square. So, that is the interesting property that you have over here. Alright, so I think that is an exhaustive introduction that completes our module on unitary matrices, that is rotation matrices, and their analog in the complex world, that is unitary matrices which satisfy the property u Hermitian, u equal to u Hermitian equal to identity, and these arise very frequently, as I already alluded to. For instance, unitary matrices arise in the singular value decomposition. They also arise in the eigenvalue decomposition of what are known as positive semi-definite and positive definite matrices, which we are going to see next. So, and these arise very frequently, and these have a very important role to play often in linear algebra, right. So, with that, let us stop here and let us continue in the subsequent modules. Thank you very much.